So let's start the recording. Good afternoon. Welcome back to class. The week 5 homework has been posted and it's due Saturday. I hope to have the week 5 quiz posted tonight. If not tonight, tomorrow, and it'll be due Tuesday. Okay. Also in the module for week 5 are the blank notes that I'm going to go over and use. You can follow along there. If, for example, I move, if you want to look ahead while we're teaching because you've answered the final prompt that I'm answering a student's question and you're like, well, what's coming up next? Or if you want to refer back to something that we talked about previously, you could either print them out or you can have them on the screen and then have blank paper. Moving forward, start getting into the habit of having something to write on and something to write with, as I will begin to ask you questions that involve more than just facts. Today we're going to look at properties of exponents, and we're going to look at function transformations, looking at the general form. Okay? Included in these week's notes is a 15 by 15 multiplication table for your reference, a list of powers ranging up to the 10th power for those numbers that are necessarily important. So for example, 4 to the 7th, you're not really going to see that, so it's not in the table. So it's not a complete table, but it's more than enough powers that you should need for pre-calculus. There's a page for a review of properties of exponents, summary of those rules, along with links to web pages that provide more information. Let's take a look at the variation problem that hopefully you're now a little more familiar with these types of problems. Jump Zone is a new fitness center for kids that recently opened in Maryland. The cost for a kid's party, including food and drinks, varies jointly with the amount of jump time a group wants in hours and the square root of the number of people in the party. Totally contrived exercise. All right. So we're reading the problem and we notice this phrase varies jointly. So we know that's going to be our equals k. And what we need to do now is to go back before that phrase and find our dependent variable. And then look after that phrase to find our independent variables, plural, because it's jointly. Jump Zone is a new fitness center for kids that recently opened in Maryland. The cost for a kid's party. So the cost is going to be our dependent variable. I'm going to use the letter C for cost. Varies jointly, so that's our equals k. With the amount of jump time a group wants in hours. So the jump time is one independence variable. I'm going to use h here, hours, and the square root of the number of people in the party. I'm going to use p for the number of people. Provide a literal equation to represent this situation. Now typically here you would write your equation and then you would fill in information to find the value of k. That's actually, finding the value of k is actually a later prompt. So here we want to write the equation with a k in it. So we get C equals K, C equals K, H, and then it says square root of the number of people, so square root of B. Right now, in the part B, it says if it costs $90 for 9 kids to jump for 2 hours, determine the constant of variation. So I'm giving you the cost, I'm giving you the hours, I'm giving you the total number of people. I want you to put in the chat what the value of k equals. Okay, so we got a lot of 15s, that's exactly right. Okay, we substitute the 90, the 2, and the 9. I'm going to simplify before trying to solve for k. 2 times the square root of 9. We apply the square root to the 9 to get 3. 2 times 3 is 6. So now we divide both sides by 6 to get a final result of 15. Describe what the constant of variation represents. Here, if we consider that one person jumps for 1 hour, the cost will be 15. So this represents the cost of one person to jump for 1 hour, $15, like the rate. Okay, now using this equation, now that we know that k is 15, Sarah's mom has saved up $375 for a party for Sarah plus 15 of her friends. If Jump Zone only rents out in 1 hour increments, how many hours can Sarah's mom afford to pay for? So I'm giving you C, you already know K, and I'm giving you P, the number of people. So what I need you to do is solve for H, the number of hours, and put that in the chat. All right, so substituting in, you should have gotten 6.25 for the value of H. Okay, but Jump Zone only rents out in time increments of 1 hour. So what this means is Sarah's mom has enough for 6 hours, but she doesn't have enough money for the 7th hour. So she's going to get some change back. She can afford 6 hours of jump time. Put in the chat how much 6 hours of jump time actually costs. That's what 6 hours of jump time cost. So, right. All right, so the question that posed is if she can only afford 6 hours of jump time, how much money is she spending? How much is Sarah's mom spending? I swear I write so much nicer than this. Okay, so the cost is going to be 15 times 6 times the square root of 16. Yeah? Square root of 16 is 4 plus 15 times 6 times 4. Let's see. I know 4 times 15 is 60. That's 60 times 6, $360. Okay, I'm doing this in my head, so I don't know what 15 times 6 is off the top of my head. It's 90. But I do know what 4 15s is, because I just remember that as being 60. So $360. So she has $15 left over. She can treat herself after spending all this money on her daughter. Okay, this is an auxiliary question there, $360. Where's my cursor? Now let's look at some properties of exponents. Evaluating the negative of -1 to the 6th power. We know that the 6th power means that the base is being multiplied by itself this many times. So we have 6 -1s multiplying, and then we have this additional negative out here. Well, 6 negatives, that's an even number of negatives. I know that result is going to be positive. So now I can ignore the negative. And then 1 to the 6th is 6. So -1 to the 6th is also 1 to the 6th, or just 1. And then this says, now that you have that result, make it negative. -1 would be my result. Well, we already talked about -1 to the 6th is 1. So multiplied by 5 is just 5. So to make sure you're not trying to multiply 5 in here first and then raising it to the 6th power. That would not be good. Okay. Because long before we were born, people determined what the proper order ought to be, and they settled on exponents first. That way, everybody does it the same way and gets the same result. Just like everybody in America agrees to drive on the right side of the road. That's just what we've agreed to. We could have agreed to drive on the left, but we didn't really like the English at the time, so we decided to drive on the right. Negative 2 to the third power. This is 3 negative 2's multiplying. Since that's an odd number of negatives, I'm expecting the result to be negative. And then 2 to the third power is I don't remember. I'm glad Mr. Powell gave me this powers table. 2 to the third power is 8. Negative 8. Simplify. Here we have an expression with multiple bases and exponents. We're raising it to the second power. One thing we can do is to write it twice, okay? Because that's what this power means. It means this entire base is multiplying itself twice. And then I can look for like bases, and I can use the associative property to rewrite the bases together. 2 times 2, well, that's just 4, right? And then I can bring the a's together and the b's together. So I have 2a squareds and I have 2b cubes. Properties of exponents say to add these exponents. 2 plus 2 is 4, 3 plus 3 is 6, giving me an ultimate result of 4a to the 4th, b to the 6th. But there's another property of exponents that says if I have a base raised to a base raised to an exponent, which is then raised to another exponent, those exponents multiply. Okay, so I have 2. Now, don't forget the 2 has an exponent of 1. So don't think of this as 2 times 2. Think of it as 2 raised to the first power. That 1 is times 2. So that's 2 to the second power. A squared, and b cubed, squared. Now, in this case, they multiply. 2 times 2 is 4. 3 times 2 is 6. Now, be careful here. I know I said using distribution, but I don't want you to confuse that with the distributive property we use when we have 2 exponents, 2 terms raised to an exponent. In which case, we'd have to write them separately, and then we'd have to use the distributive property to multiply each term by each term, okay? So if I have a plus here, so I have 2 terms inside this parentheses, I cannot use this distribution the way I did here, distributing the exponent to the exponents. That's only if I have 1 term. Now, if in multiplication, if I have a base raised to, in multiplication, we added the exponents, a squared times a squared, we add those exponents. Then in division, we subtract them. We know 6 divided by 3. Then I have x to the 5 over x to the squared, so that's x to the 5 minus 2. And then y to the 2 minus 7. We can simplify that. Because 5 minus 2 is 3, 2 minus 7 is negative 5. I will typically ask you to write your final answer with positive exponents. We will use the negative exponent property here to rewrite this y, which is in the numerator, in the denominator, which then changes the sign on the exponent from negative to positive.
Well, I have a question. Where did you get 2?
All right. This is really all review. You've done some of this in Algebra 1, and you've done a lot more in Algebra 2. If you need additional practice, that's why I have this Maths is Fun here. You can click on this, and this has additional examples for you to practice. Khan Academy has them to ad nauseum if you need to practice. You can just say, hey, Mr. Powell, I want to practice this on Khan Academy. Can you give me a link, right? So that way you don't have to search yourself. I'll do that for you. So let's use these properties of exponents to rewrite our expression using a different base. So we have 8 to the 4th. I'm asked which of the following is an equivalent expression for 8 to the 4th power. I look at my possible answer choices, and I notice that all of those bases are 2's. So what I want to do is to rewrite this 8 as 2 to some power. Using that table before, or up here when we already did it, we see that 8 is 2 to the third power. So I can rewrite this 8 as 2 to the third power inside of parentheses because I'm substituting. And then I just have the 4 on the outside. And then what would be the result? Okay, and I'm going to launch a poll here, and then I want you to give your answers as we move through. Okay, so for poll question number 1 says, what is your response to question 4? Is it A, B, C, D, or E? In number 5, it says, which of the following is an equivalent expression for 25 to the 3 halves? Here, we notice all our bases are 5s. So we want to rewrite this 25 as 5 to some power. And then we're going to multiply the 2 exponents just like we did up here. In 6, now we have a radical. In Algebra 2, I believe you're taught that radicals can be rewritten as fractional exponents. So 32, the third root of 32 is the same as 32 to the 1/3. Ugliest 32 ever. 32 to the 1/3. But all our answers have 2 as a base. So we want to rewrite 32 as 2 to some power. 2 to the 5th is 32. And now I just need to multiply those exponents. Similarly here, we have 27 that can be rewritten as 3 to the 3rd power. We have a radical here, so that's 3 to the 3rd power raised to the 1/4. Okay, we can multiply here, but we notice that our answer choices, they're not in the denominator. So we need to use the negative exponent property to rewrite this base in the numerator, which then changes the sign on the exponent. Okay, so I have 2 minutes into the poll. Let's take another 4 minutes, and then I will end the poll. You learned about this value D as being your translation up and down. You learned about this, although it probably was labeled as K. Definitely for absolute value and quadratic equations. You learned about this C, which was H for you, but it was X minus H. In this general form, we're just gonna make it plus, okay, which will reverse the value that you would expect for left and right, but we're gonna flow with it. You're even familiar with this A. I'm sorry, the C was a move left or right. You were familiar with this A. The absolute value of A, if it was greater than 1, it was a stretch vertically. If it was between 0 and 1, it was a shrink. And if it was negative, that was a reflection in the x-axis. But this value B, you weren't really familiar with until you got to sinusoidal functions, where you had to stretch or shrink your sine function to fit the data as accumulated, right? So you had your phase shifts, but you also had your stretches and shrinks. So those are all of our parameters. So here I have a function f of x, and here I have different transformations of f of x. And I picked a piecewise function so we wouldn't get hung up too much on, oh, quadratics. What do I remember about quadratics? It's just about transformation. And what we're going to do here is we're going to try to figure out what's going on with the function. And to do that, we're going to pick a point in what we will call the pre-image, like in geometry. And we'll look at the image and we'll say to ourselves, well, what happened since that the image is different from the pre-image? Looking at the overall shape, it kind of looks like it just moved to the left. How far though? Well, if this is at 0, 5, and this is at -3, 5, it must have moved 3 to the left. So that's our description. It moved 3 to the left. We call that a translation. We can verify this by looking at 2 other points. So here's a point 4, 2. Now, instead of asking what happened, Let's apply the rule and see if that's what actually happened. So 4, 2, move, translate 3 to the left, I would be at 1, 2. Look down here at the image, and I'm at 1, 2. Awesome. Here's another point. Negative 6, 2. If I translate that 3 to the left, I should be at negative 9, 2. I look at the image, negative 9, 2. Awesome. So given a pre-image and an image, you should be able to describe to me what happened in this transformation. Here's another one. If I consider the point 0, 5 again, it looks like the image is at 0, negative 5. Now just looking at using our intuition, it looks like, oh, these are different because this is like upside down. Upside down. In geometry, you remember that upside down is as the result of a reflection. So we're going to say it's a reflection. But what is it reflecting over? We know we need that line. So let's take a look at the distance from the pre-image to the image. And we know that the point of reflection is halfway between. So the distance from the pre-image to the image is 10, right? Because I'm going from 0, 5 to 0, negative 5. Half that distance is 5, so that would put me at 0, 0. That's the halfway point. If I look at the purple, I went from 4, 2 to 4, negative 2. Well, the halfway point is 4, 0. And if I look at the blue point, I went from 6, positive 2 to 6, negative 2. Those points are also 4 apart, and the halfway point is 6, 0. That means if I connect those points, this is my line of reflection, which in this case happens to be the x-axis. So we reflected over the x-axis. Finally, if I look at this image, well, this one kind of looks like this one, what moved over. So let's try to match the pre-image with the final image. And we could say, well, I reflected over the x-axis. That would have put me at 0, negative 5. And then looks like I got to move 2 to the right and up 3 to get to the current point. So it's a combination of reflection and then translation. I'm going to write down my description, excuse me, and then I'm going to check to see if it holds for the other 2 points. So here's my purple point. I'm going to reflect it over the x-axis to 4, negative 2. And then if I move 2 to the right and then up 3, do I get to the correct point? I do. Finally, the blue point. If I reflect, I'd be at negative 6, negative 2. And if I move 2 to the right and up 3, I'm at my current point. So that rule holds for the 2 other points. Now, you'll notice that or maybe you didn't notice, that I said reflect first and then the translation. Could I translate first and then reflect? Well, it turns out, let's take a look. So there were 3 things going on. There was the reflection, there was the move to the right, and then there was the move up. What if I put the move right prior to the reflection? Right, so here what I'm doing is I'm going to take this right 2, and I'm going to make it first, then I'm going to reflect, and then I'm going to up 3. So here I am at 0, 5. I'm going to move right 2 to 2, 5. Then I'm going to reflect. That would put me at 2, negative 5. And then if I move up 3, I'm at 2, negative 2. Okay, so I could have done the right translation first and then the reflection. What if I move up 3 first? If I move up 3 first, I go from 0, 5 to 0, 8. Then if I reflect over the x-axis, I would be at 0, negative 8. And then if I move 2 to the right, I'm in the wrong location. So we don't want to do the reflection prior to that translation up. And there's a reason for that. And let me break that down for you in a second. Notice that this reflection resulted in a movement in the y direction. The translation up also resulted in a move in the y direction. So what we're discovering is if there are multiple moves in the y direction, it does matter which one happened first. But this move to the right is a move in the x direction. It was not affected by these two moves in the y direction. So that's why it didn't matter that I did this first versus last. It wasn't affected by these two moves in the y direction. And the reason that is the case is because if you think back to when you studied the exponential function and you had to draw this exponential growth, you noticed that there was an asymptote of y equals 0. Y equals 0 was the asymptote for this function. But when you shifted this function up, it also shifted up the asymptote. Which means then, if I'm going to move up 3 first, I need to move the line of reflection up 3. So if I move up 3 to 0, 8, I need to then reflect over the line y equals 3 to go from 0, 8 to 0, negative 2, and then move right 2, and then I'll have the right location. Now, because that's a lot to remember, if I reflect first, I got to move the line of reflection before I then move again in that direction. I'm just going to say, do the reflection first if there's a translation in that direction. So if there's a reflection in the x direction, there's a reflection in the y direction, and there's a translation in the y direction, do the reflection first. That way you don't have to worry about moving the line of reflection. Now let's take these descriptions and write a rule. Okay, so the first skill is given a pre-image and an image, can you write the description? An associated skill, not mentioned here, is if I give you the pre-image or the image, and I give you the description, can you give me the other one, right? So if I told you this was the image, and it was the result of a reflection over the x-axis, you should be able to create the pre-image by undoing that reflection. The final associated skill is writing a function rule from the description. If I give you a function rule, you should be able to give me a description. And if I give you the function rule in either the pre-image or the image, you should be able to give me the other. So if I give you the rule in the pre-image, you should be able to give me the image. If I give you the rule in the image, you should be able to give me the pre-image. And in both cases, you should be able to give me the description also. So that's a lot. That's a lot of moving parts. Translation to the left. You need a C value here. And it's x plus 3. Okay. You'll remember from Algebra 2 class that this was x minus h. And then you said, well, if I move 3 to the left, then h is negative 3. Or then I had x minus negative 3, which is x plus 3, which is what I have here. But in this case, since it's not an x, h, it's a c, the value of c is positive 3, because it rhymes. Reflection over the x-axis. That's when the a is negative. So if I take f of x and I make it negative, I get negative f of x. And then reflection down over the x-axis, so I have the negative. And then a translation up 3 and right 2. Well, right is the opposite of the left direction, so that's why it's negative here. And then up 3. These transformations are called rigid transformations. You may recall these from geometry. Those rigid transformations were translations, reflections, and rotations. Objects will keep the same shape and size after any rigid transformation. Okay. So back in geometry, you had a triangle. You performed a rigid transformation on that triangle to get a congruent triangle. And then once you had those two congruent triangles in the first quarter, in the second quarter, you started with the triangles, and then you had to prove that those two triangles were congruent because they were the result of a rigid transformation. First you did it with transformations, and then you did it with information about the triangles themselves. Now if I just look at this function rule here, and I say, well, let's say x was 7. Well, in applying the rule, the first thing I would do is subtract 2. So the first move is actually right 2. Then the negative is applied after the function. So then there's the reflection. And then finally the move up. So if I'm looking at the function rule, the move up is actually the last thing anyway. And it happens after the reflection. I want to look at one example that's rather involved. Nope, I'm going to give you a review first of the properties. And I want to look at one example that's rather involved to see how this is implemented. All right, so we have the function a f of b of x plus b x plus c plus d, where our parameters are a, b, c, and d. D is a translation up if d is positive, and down if d is negative. C is a translation left or right. Now, D is rather intuitive because if D is positive, and you know it's a y direction, you know going up are the positive y's. The y gets increasingly positive. So that makes sense. However, for C, when C is increasingly positive, that's actually a move to the left. So that's kind of against our intuition. When C is positive, we're actually moving in the negative direction. And when C is negative, we're actually moving in the positive direction. Now, a vertical stretch, that was our A value. When A is greater than 1, we're stretching away from the x-axis. And that stretch factor is A. When A is between 0 and 1, and here I'm talking about the absolute value of A. I'll get to the negative part in a second. So we're just saying if A is between 0 and 1, we have a vertical compression. Now the actual factor, okay, well, let's do this. By a factor of A, okay? So whatever that number is, if that number is greater than 1, it's a stretch. If the number is between 0 and 1, it's a compression, okay? And you use that value of A. But if A is negative, we have a reflection over the x-axis. So there are two parts here. So if A is negative, we'll say the negative part is a reflection of the x-axis. Then we'll ignore the negative and look at the actual value of A to see if it's between 0 and 1 or if it's greater than 1. B, and that makes sense, right? So if A is a big number, 5, we're expecting our graph to be bigger. It's actually the opposite for B. When B is big, it actually makes the graph compress, which is a little against our intuition, okay? It's almost like if your little brother, let's pretend you had a little brother, he's running a race, right? B is like giving him a little boost, right? If I give him a little boost, then he doesn't have to, if I give him a skateboard, then he doesn't have to work as hard to go the same speed. And that's what B is doing. B is like giving your little brother a boost, so he, the X, doesn't have to work as hard to get to the same distance, which is the Y value. So it compresses. X has to do less to get to the same Y value. When B is between 0 and 1, it's a horizontal stretch. Okay, that's like your little brother's running a race, but he's trying to be quiet so his mom doesn't hear him because he's actually running through the house. Right, so he's going to run slower. It's going to take him longer to get the same distance. And then when B is negative, it's a reflection of the y-axis. So A and D, we're kind of going with our intuition. When A is big, the graph gets bigger, it stretches out. When D is positive, it goes up, and when D is negative, it goes down. So that kind of makes sense. With our intuition. But B and C were the opposite of what we thought. Finally, see this F? This F is the function itself, f of x. It is the expression that changes our input into an output. You can see from the general form that B and C are applied to x prior to the function, which means B and C will alter the domain of our function because it's being applied to x, which are all of the values in the domain. Then after the function is applied, then we multiply by A if necessary, and then add D. So A and D will affect our range. All right, so I'm going to post this as a summary of what you remember from last year. That's why I'm kind of going pretty fast. Right, a lot of this stuff is algebra 2, but I want to kind of go over it before we get into what we're doing in pre-calculus.